Okay, so I'm gonna disable the chat for now, right? Ah.
Okay, hi everyone. Welcome to chemistry, and we're really excited for all of you to be participating in this Kid Teach Kid summer camp. And before we begin with our chemistry class, I just want to quickly make a few announcements about the resources page, questions, and how to submit surveys and things like that. So let me quickly share my screen. Okay, yeah. So the first thing to note is that if you're ever looking for like resources such as lecture notes, where the homework is, or supplemental material, you can just go to our website, and the link is right here. Or you can go to classes and then summer camp class resources, and you'll be sent to this page, which has all the subjects as well as all the material that we've prepared for you guys. And then the next thing is, if you ever have questions after the class, then you can just go to classes and then student question submission, which is right here. And it should send you to this page, and you can just fill out all the information, and we'll get back to you as soon as possible. And lastly, we really appreciate any feedback that you have on our classes. So if you ever have any time, then feel free to fill out this quick survey about our classes. And yeah, you can find this by going to classes and then student survey. And that's all I have for now, so yeah.
All right, thanks, Rich.
Sorry, yeah, I was just gonna say something real quick. For those of you guys who didn't go to my class yesterday and may not know about what I wanted to talk about, so let me just share my screen real quick. Okay, so basically what happened was I recently wrote a book called Epidemiology Unmasked, and if you took my public health class, it's highly recommended that you get this book to go along with it. And also, it's like I spent quite a lot of time on it, and all the proceeds are going to be going to help donated to the COVID-19 workers. And also, it's been endorsed and reviewed by a few professors and public health professionals. So I would really appreciate it if you could get it. The ebook is preferred because it's cheaper, and also you don't have to wait a long time for shipping. So yeah, and then also if you go to the website kidteachkid.org and then /epidemiology-unmasked, then you should be able to find all the information about that. I guess I can just go ahead and put that in the chat real quick. So okay, so you guys should have gotten the chat, the link in the chat. So please check that out if you have time. And also I would really appreciate it if you could invest like, I don't know, $4 into buying that book. It would help me a lot. Thank you so much, guys.
Okay, awesome. So I'll start sharing my screen. Okay. Cool. So welcome to chemistry class, guys. This is my first time teaching. My name is Yitian, and I do Scioli and I do Chemoli. So the purpose of today's class is that I want to teach you something interesting or something that you can walk away with, but it's not necessarily something that you'll see in high school or middle school classes. Instead, these are pretty important subjects that you won't see in your high school and middle school courses. I actually think that the science teachers at school do a really good job, so I'll leave those portions to them. But today I'm going to be talking about things that you won't necessarily hear from them. So as you probably have noticed, I did disable the chat, but actually we'll be using the chat for discussions during this class. And so periodically I will enable the chat. And also every once in a while, I'll stop and ask you if you have any questions for me. And that will happen probably every couple of slides. So I guess we'll get on with the class. Like and subscribe, guys. I'm just kidding. Please pay attention, though. Okay, so today's topic is going to be about light. And you might be wondering, wait, what? I thought this was a chem class. Why are we studying light and stuff that will happen in physics? But the thing is, it's really important to start off with a foundation in physics, especially because it's important to study energy. And since chemistry is the interaction of matter and energy, you need to understand both parts. And also, we will get into things like the colors of chemicals, and that has to do with light. So today, we're gonna be talking about four important things, which is in the class overview on the right. So first of all, light is two things. Whether you glow in the dark or not, you'll be surprised at the answer. We'll talk about how heat vision goggles work, and we'll also talk about the beginning of quantum theory. And the beginning of quantum theory is super important because quantum theory is used to model atoms and such. All right, so let's start with the first thing, which is that light can be two things. Light has wave-particle duality, and duality means that there are two ways you can describe light. Light can be described as a wave or as a particle. So as a wave, it can be an electromagnetic wave. So the light wave has an electric field, and it's going up and down in this picture. Has a magnetic field that's traveling with the electric field, and it's moving from side to side, and both of these waves propagate forward. The electric and magnetic field are perpendicular. Now, that's kind of important to know. Also, my junior high teacher said that scientists are not creative in naming things. And that's why they kind of took electric field, magnetic field, kind of jammed them together like a car crash and gave it the name electromagnetic wave. Awesome, so now we're gonna talk about photons and how light can also be a particle. So at the quantum level, at the really, really tiny level, a photon is a little package of energy in the form of light. And so photons are discrete, meaning you can have 1, you can have 2, you can have 10, you can have 10,000. You can have a whole number, but you can't have something in between. You can't have 0.45 of a photon. You can't have 0.42 of a photon. You can't even have 10 and a half. So at this point, I'm going to check the Q&A and see if there's anything. Okay, homework, I don't have any homework for y'all because the point of this class is for you to take something away and just understand. Maybe next time I'll assign, I don't know. Okay, those are interesting. Are we studying physics in 2 hours? No, you're not gonna learn all of physics. This is just the physics foundation that you need to learn chemistry. Okay, the rest of these questions are very interesting. So we're gonna move on to measuring wavelength. All right, so what is wavelength? Well, wavelength is how long a full cycle of a wave can be. So as you can see, you can divide a wave into certain segments, and these segments repeat over and over and over again to construct your wave. So you can measure wavelength from the middle of a wave to the next time it's the middle of the wave. So look between the green lines, and that is a wavelength. You can also measure it from peak to peak. As you can see, it's from the top of the wave, which is the peak or the crest, and then the next time it's at the top. Or you can measure it from trough to trough. So from the bottom of a wave to the next time it's at the bottom. Also, wavelength is denoted by the Greek letter lambda, and it looks like an upside down Y. You can see it in the bottom right corner of the screen. And also it's in the units of meters. So it's in units of length, right? Like in meters or millimeters or centimeters or nanometers. Let me check the question answers so far. No, we're not going to be doing amplitude today because it doesn't really have to do with the calculations that I'm going to ask you to do. By the way, I know that I said in this class we'll be using a calculator. If you guys have a calculator, that would be great. Also, I think it's better if you guys just, yes, we will learn frequency and speed, and those are the next slides that I'm going to go over. Also, instead of raising your hands, just type directly in the question and answer box, and I'll check. What type of calculator should we have? Literally any calculator that lets you do scientific notation. All right, so I think we can move on to frequency. Okay, there we go. So frequency is a unit of measure that answers how many full cycles can pass a single point in 1 second. So if you look on the diagram to the left, I have these 4 cycles of a wave. So 4 units, that's 1 point, which is a green line. Okay, show you again. In 1 second, 4 cycles passed 1 point. So because of this, the frequency is 4 in this example. Frequency is denoted by mu, and mu is another Greek letter. It looks like the letter V, but it's actually mu. Let's see. Oh, also, it is in the units of inverse seconds. Now, you might think this is really weird. How can I have an inverse second? But let's look at this example. So, in this example, 4 cycles of a wave passed per second. So, because of the per second, the frequency is expressed in inverse seconds. Okay, so I'm going to check the question box right now. Are we going to use sine and cosine? No, we're not today. Will you send a video of the seminar? It's getting recorded right now. The middle part of the wave, well, I don't know that there's a certain name that we need to use for it for this class. So, so there is, yes, there's trough, which is at the bottom of the wave. There's crest, and that's at the top. And then there's also the middle of the wave. And we're not going to use that term in this class today. What is an inverse second? It's like 1 divided by seconds. Now that sounds really weird, but the only reason that we're using inverse seconds is because 4 cycles passed per second. How is this related to chem? Well, you'll see later. Square waves, we're not dealing with those. We're not dealing with those, sorry. Okay, so next slide. So one important equation that we need to deal with is the light speed equation. And so the speed of light is a constant value. It's a huge number. It's 3 times 10 to the 8, so 3 with 8 zeros trailing behind it, so a huge 9-digit number. And it is the same number no matter what. So all light should travel at the same speed as all other types of light. It does not matter what type of light it is. And as you can see by the equation, the speed of light is equal to the wavelength times the frequency. And so this makes sense if you think about how speed is the distance covered in 1 second. And the frequency tells you how many cycles pass in 1 second. And the wavelength tells you how long is a cycle. So essentially, when you multiply the two together, it's how much total distance is covered by the light in 1 second. Let me check the Q&A real quick. Yes, the inverse second is the reciprocal of seconds. Oh, you're getting the questions in by typing the questions, and I'm just answering them live. So is the speed of light exactly 3 times 10 to the 8? Well, okay, technically it's like 2.9998 or 2.998. So no, it's not exactly 3 times 10 to the 8, but it's pretty darn close. What is hertz? Okay, so hertz is the unit for inverse seconds. I probably should have said that during the previous slide, but hertz is the name for the unit of inverse seconds. All right, does the speed of light change when it passes through different objects, air, or water? Well, I don't think so. When it passes through air or water, it can bend the light, but it does not necessarily change the speed of light. It's not like sound, because sound travels at different speeds in different objects. So yes, 1 hertz means 1 inverse second, which I explained as 1 per second. Lambda, that's how it's pronounced. And does the speed of light change when encountered by a black hole? I don't know. Don't ask me about black holes. I do chemistry, not astronomy. And yes, this is getting recorded. All right. Oops. So now we're gonna, oh, bad PowerPoint. Okay. Now we're gonna talk about the energy, the light energy equation. So remember the photon that we talked about and how it was a little packet of light? So this equation tells you how much energy is in that packet of light. And this equation is really important because it relates the wave and particle properties. In the previous slides, we were talking about the wave properties of light and how it has the frequency, how it has the wavelength. Now we're taking those wave properties and putting it into a particle representation because it talks about how much energy is in that little particle. So this equation is E, energy, equals Planck's constant times the frequency. Remember we talked about frequency in a previous slide, and Planck's constant is a super tiny little number, and Planck's constant stays the same no matter what. So we have 2 numbers that stay the same no matter what. It's first the speed of light, and second Planck's constant. The speed of light is a huge number, while Planck's constant is a really tiny number. It's like 0 point, and then you have like 33 zeros, and then 66262. But we write it in scientific notation to make our lives easier. All right. So in this slide, we're going to have a little bit of practice. The question is, a particle light has energy 4.47 times 10 to the negative 19 joules. So what's its frequency, wavelength, and color? I'm going to check the Q&A real quick. Does the speed of light change when in space compared to on Earth? No, it's the same. It's, remember, speed of light is a constant. Okay, H, I think we just talked about Planck's constant. And, oh, Okay, somebody asked what is the unit of joules per second. So I'm gonna go back to the previous slide. If this will let me know, it won't let me. There we go. Okay, so it says joules per second, and that's because energy is expressed in joules. Joules is the unit for energy. And why is it joules times second? Well, that's because the frequency, which is in hertz, which is in inverse seconds, well, when you multiply a second by an inverse seconds, then it cancels out to 1. It's not a dot product, it's a multiplication sign. Is this related to E equals mc squared? We're not talking about that in this class. Okay, so what are joules? No, it's spelled Joules, and it's a unit of energy. We're not talking about the glass pyramid today, although that is really cool. Okay. All right. So right now I'm going to open up the chat box and let you guys discuss for a couple of minutes what you got for the practice answer. So, all right. So in the chat, please use your calculator to do the practice problem and tell us what you got for the answer. All right, I see one answer. You guys, please only type what you got for your answers or ask questions to your other friends in the class. All right. So a lot of you guys are getting some pretty good answers, and I'll tell you guys what the real answer is in a second, and we'll work it out together. Okay, so people asked, is the color blue? Well, I don't know. Well, I do know. The spoiler will come later. It's in the presentation. So is this related to E equals mc squared? Well, E equals mc squared is actually mass to energy conversion, and we're not talking about that in this class. Okay. So I'm turning off the chat now. A lot of you guys got some pretty close answers. So let's talk about how we do this problem. Okay. So that is the frequency, and a lot of you guys got pretty close. What did we do? Well, we knew that the energy was Planck's constant times the frequency. So we just took the energy that we gave in the problem, so 4.47 times 10 to the negative 19, and we divided it by Planck's constant, which is the little h. And so that's how you get frequency. Now you use the next equation, the second equation on the right, to and you take the frequency, and then you take the speed of light. Now you take the speed of light and you divide it by the frequency to get the wavelength. So the wavelength was about 445 nanometers, and notice how 445 ends up in the range of blue. So the answer is blue, yes. Somebody asked, what are the numbers on the wheel? That's a really good question. So on the color wheel, you have different wavelengths of light. And this is only for visible light, which is a tiny fraction of the spectrum. But these different wavelengths of light are the different colors that our eyes can perceive. Okay, so this is the entire electromagnetic spectrum. So these are all types of light. So as you can see, you have radio waves, which are the largest wavelengths. And now remember back in our equation how large wavelengths have small frequency because they're inversely related. Inversely related means one increases and the other one decreases. So if you look back at the equation, the speed of light equals the wavelength times the frequency. If the wavelength gets bigger, then the frequency has to be smaller. And then as you go down the electromagnetic spectrum, you get into microwaves and infrared waves and stuff, and their frequency and their energy starts increasing. You also saw that in the E equals Planck's times the frequency, that as the frequency increases, then the energy also increases. So as you go down this chart, your energy and your frequency increase, but as you go up the chart, then your wavelength increases. So as you can see, the visible light is only a tiny, tiny part of the entire electromagnetic spectrum. And as you go down, the wavelength gets smaller and smaller, as I've said before. In fact, at the top, when you have radio waves, the wavelength can be about as tall as a building. But then at the bottom, where you have gamma rays, the wavelengths are about the size of an atom's nucleus. So it's a very, very diverse range. Okay, this is a question that we're going to talk about with our chat, and you guys can discuss. Do you glow in the dark? Okay, so we're seeing a lot of yeses. We're seeing a lot of no's. Okay. Somebody said it depends on the wavelength. No, please don't drink glow sticks. Whoever said that, that's not healthy. All right. So I've closed the chat box. So do you glow in the dark? Well, the thing is, some light is detectable by the human eye, and some light is not detectable by the human eye. So the answer is technically yes, you do glow in the dark, but mostly you glow light that you can't even see. Because remember the huge electromagnetic spectrum, and remember how only a tiny slice is visible? Well, the light that you glow is not detectable by your eye. So that's kind of sad. We don't have glowing kids running around. And so now Wilhelm Wien, who is a really intelligent scientist, related the temperature with the wavelength that you glow. So lambda max is the wavelength of light that you emit mostly. So it's the wavelength of light that you emit with the most intensity. And he said, well, you can emit light at multiple different wavelengths, but the one that you emit at most is lambda max. And it depends on the temperature, as you can see in this equation. At the bottom, notice it says that it only applies perfectly to something that absorbs all light equally. Well, something that absorbs all light equally does not exist on Earth. So, because it means that it does not prefer to emit a certain wavelength, and it does not prefer to reflect a certain wavelength. And so, if it doesn't prefer any sort of light, then the temperature now has the power to alter the wavelength of light that it emits. So unfortunately, it doesn't exist on Earth, but things can get pretty close. And so why does it not exist on Earth? Well, if you think about a kid wearing a red shirt, for example. Well, the kid wearing the red shirt, he is absorbing lots of different light, but he is not absorbing red light because of his red shirt, right? So is all light absorbed equally? No. But however, this equation can get pretty darn close to, well, this equation can get pretty darn close, even though nothing fits its requirements perfectly. So let me check the Q&A. So somebody said, isn't this called black body radiation? That is exactly correct. Why does the constant have units of km? It's actually not kilometers. It's degrees Kelvin times meters. So it's 2 units multiplied together. What is K? Well, K is degrees Kelvin, and it's a measurement of temperature where 0 starts at absolute 0. Why is it lambda max? Well, that's because Wilhelm Wien said that you could emit light at multiple different wavelengths, but only one is the maximum. So only one wins out over the others. So what are kelvins? Well, you know how you have the Fahrenheit and the Celsius scale, right? So the Kelvin scale is similar to the Celsius scale in terms of how big is each unit of temperature. However, the Kelvin scale, well, the Kelvin scale, the 0 starts at absolute 0. On the other hand, the Celsius scale 0 is at the freezing point of water, which is not absolute 0. And so the way you can convert between Celsius and Kelvin is that 0 degrees Celsius is equal to 273 degrees Kelvin. Let me check the Q&A. So now I'm going to tell you how does it work when you glow in the dark. Because you saw the equation, but how do we know the equation's true? Well, first of all, this is how this is a qualitative way to think about it. So I'm not giving you how to derive the equation because even I don't know how to do that. But if you think about it using logic, it kind of gives you an explanation. So first, anything that is not at 0 degrees Kelvin has energy. Remember that in this slide, the temperature of the object was expressed in kelvins and 0 was absolute 0, which means no heat energy. Well, if you use a 0 in the denominator, then this equation totally doesn't work. So first of all, you need to have a non-absolute 0 temperature. And that means you have heat energy. And when there's heat energy, then molecules start moving. And once molecules start moving, they can get excited like this cartoon child right here. Well, if you're excited, then you want to release energy, right? So the same thing occurs with the moving molecules. And the excited molecules can release a photon, which is, remember, a little packet of light and energy. So here's your little photon that gets released. Let me check the Q&A. Is it possible that our eyes mutate to be able to see all light? Not yet. What color do we emit? Well, we're gonna figure that out in a calculation that you guys are gonna do in the next slide. All right, so we're gonna talk about heat vision, which is super cool. So in this calculation, you get to figure out what wavelength of light does a human body at 37 degrees Celsius emit. And that will answer sort of what color do we emit, but technically it's not really a color that you can see with your human eye, because remember, it is outside of the visible range of light. So let me open the chat. You guys can discuss what do you think the answer is to this question. Remember, this question, well, yes, somebody said 37 degrees Celsius is 310 degrees Kelvin. All right, so great, you converted it to Kelvin. So that was actually the first step. So now you have to use kelvins in your calculation using Wien's law. It looks like some people are getting it. So does K equal T? Well, T is the temperature, right? And kelvins is the units of temperature. And so sort of, but not really, because temperature is temperature that you're supposed to plug in to the question. And K is Kelvin, which is the unit that's associated with the temperature. So yes, K is a unit and T is the temperature that you're supposed to use. So in this calculation, you would be using 310 for your letter T. Okay. So I see a lot of people are saying red. Well, we'll see once we finish the calculation. No, km is not kilometers. K is degrees Kelvin and m is meters. So they are two units that are totally different. They don't have anything to do with each other than that they're multiplied together in this scenario for this constant. All right, so now I'm just seeing a lot of spam and it doesn't seem like anybody's, M is the unit, yes, M is meters. So some people have been getting it right. A lot of people are just spamming right now, so I'm going to turn off the chat. Okay. So you guys know that you have to convert the Celsius to kelvins. And in the second step, you use the equation above and you plug it in. And so the answer you get is 9,355 nanometers, or 9.355 times 10 to the negative 6 meters. So this was the answer that I saw somebody type in chat, so congratulations. And yes, this is in the range of infrared light. So everybody was saying red, red, red. Well, it wasn't red light, it was infrared light. As you can see right here, the range of infrared light is between 780 nanometers and 1 millimeter. So the answer that you got was greater than 780 nanometers, but it was also less than 1 millimeter. So it ended up in the infrared region. And unfortunately, we cannot see infrared with our eyes, but heat vision goggles certainly can. And that's how heat vision goggles work. The energy released as light, released as infrared light, can be detected by these heat vision goggles. How do you get 9,355 nanometers? Well, let's go back to the previous slide. So when you took the 0.0029 and you divided it by 310, then you got the answer of 9.355 times 10 to the negative 6 meters. And because of unit conversions, 1 meter has 10 to the power of 9 nanometers. So you just took the 9.355 times 10 to the negative 6, multiplied it by 10 to the power of 9, and you got 9,355 nanometers. And so I just talked about how heat vision goggles work. As you can see, there's a little picture of a mouse, and some parts of the mouse have a little bit higher temperature, like near the face, near the brain, because that's where all the blood flow goes. And that's why it releases a shorter wavelength of infrared light that can be detected by the goggles, whereas the tail is less warm, so it releases a different, a longer wavelength of infrared light. The top picture of heat vision goggles is from Roblox, because I thought you guys would find that funny, and the bottom picture is actual heat vision goggles. So let me check if there's any questions. There's awesome. So now we're going to talk about the ultraviolet catastrophe. So remember how in the previous slides we talked about the maximum wavelength, and that was the wavelength that's mostly emitted. There's some other wavelengths that that the scientist Wien, he said that could be released, but Wien's law says that, well, you can emit light at every wavelength possible. Only some of them are more than others. But that would technically mean that you would be emitting UV light, X-rays, and gamma rays right now, and that's not possible. If you emitted UV light and X-rays and gamma rays, then there would be no life possible on Earth, and that is not good. I don't want to have a friend who emits UV light to give me skin cancer. So the scientist Max Planck, he decided, well, maybe you can only emit a certain type of light if you have enough energy to release that light to begin with. And so in this sense, he used quantizing light, and that's where quantum physics was born and quantum theory was born. So a fun fact that I put on the slide was that when he quantized light, he thought, well, maybe I was just using a mathematical trick and it somehow worked, but I don't know that it's true, and I don't know that if it was accurate. But it was actually accurate, and that's how the entire field of quantum theory started. And he also got the Nobel Prize for it, which was pretty cool. So next slide. I'm going to use the analogy of a ramp and stairs to show you what is quantization. So the first thing you need to know in this analogy is that the higher you are, the more energy you have. So if you're on the top step or if you're at the top of the ramp, then you have lots of energy. And then falling down the ramp or falling down the stairs releases energy. So in the classical model, they said, well, you can be at any energy level that you want, and you can be on any position of the ramp. And so there's this little guy, and he can be at any position on the ramp. But as you can see, the classical model could not explain everything. For example, it couldn't explain the ultraviolet catastrophe, right? And so you needed a new model to model it. And that's where the quantum model came in, and that's what Max Planck came up with. So the 20th century new physicist came and said, well, at the tiny molecular scale, the continuous spectrum, it breaks down, and it breaks down into stair steps. And so you can be on any stair step, you can be on this stair step, you can be on this stair step. So that means that you can only exist at specific energy levels, but you can't be somewhere in the middle of two energy levels. You can't be halfway. So I kind of want you guys to make a connection with the photon, right? You can be at one energy level or you can be at another one, but you can't be halfway between. Similarly, you can have one photon, you can have two photons, but you can't have like 1.5. So this is not possible. He cannot be floating in the middle of two stairs. Okay, so next slide. Max Planck said that the only way to emit UV light was to release a ton of energy. So as you can see, there's from the top step to the bottom step, that's a huge energy difference, and that would release a lot of energy. But remember from the equations we discussed earlier that UV light contains a lot more energy in its photons than infrared light. But what if the temperature is not enough to become UV light? So that means that you'll have to emit infrared light, right? Because you're not that hot. Like, face it, kids, you're not that hot. And you only have enough energy to get to the second stair step. There's not enough energy to launch you up the steps and all the way up to the top where you would be able to emit UV light. Because it takes heat energy to go up the stairs. And it takes a big burst, so high temperatures, lots of energy, to jump up the stairs and get to the top. So if you don't have enough energy, then you can't be excited up the stair steps to the top. So that's why the classical model is inaccurate. Because if any single energy level is okay, if you can be at, if you can be at like half a stair or 3/4, then that means that any temperature can technically continue to excite the molecules to a higher energy level, bit by bit, all the way to the top. But that means that technically it's possible to release the UV light, but you don't see little children releasing UV light and giving everybody skin cancer. So this model is not correct. Because remember how a stair step requires a big input of energy? Well, for the ramp, you can just put an infinitesimal tiny amount of energy and it would technically push you up the ramp a little bit. And over time, it would push you up all the way to be enough to release UV light. But the stair step is more accurate because you can either get onto the next stair or you can just not get on. It's there's no gray area where you only get to go up half a stair step. So see, the classical model does not work for quantum physicists. I'm gonna check the Q&A right now. What is the range of the color white and black? Well, here's the thing. White light is all sorts of different visible light combined together. Whereas for the color black, it's the absence of light. So if there is no light getting emitted, then it looks black to our eyes. How hot would you have to heat something for it to glow red or violet? We're actually going to do a calculation for that in the next slide, so hang on. Will you die if you have that huge amount of energy? Well, if you were able to, if everything in the world released UV light and gamma rays and X-rays, you would not exist. You would not even be able to be formed. Life would not be able to evolve. Would you go higher up the stairs if you burned up a higher fever? Well, you would not be able to release UV light if you burned a higher fever, but you would be able to release a little different wavelength of infrared light that can be detected by the heat vision goggles, but only by a little bit. It won't be, it won't go all the way from infrared to UV. If we cook something hot enough, it will release gamma rays and kill every one of us. Well, you would have to cook it up to really high level, really high temperatures, like hotter than the stars, hotter than a bunch of stuff. So you can't cook things that hot. I'm sorry. Black is no light, correct. Would your skin crack if you got heated that bad? I've never tried. I don't want to try. When are we going to use our calculator? That's when I give you practice problems. Great. So finally, we're going to have another practice problem. How hot is this star? The peak wavelength of light released by this red giant star, Aldebaran, is 741 nanometers. So how hot is it in degrees Kelvin? I'm going to open up the chat for you guys to submit your answers. I think somebody already got the answer, maybe? Is this physics class? No, well, we're using chemistry because we're using physics in chemistry class because it's the foundations. All right, a lot of you guys are getting the correct answers, and I'll turn off the chat right now so that we can discuss. Okay, so let's see. The answer is about 3,910. When I did it with my calculator, I got 3,913. So all of y'all who said 3,913, yes, you're correct. All I did was round to 3,910. How did I do it? Well, you have to take the 7.41 times 10 to the negative 7 meters, and that's your lambda max. And then you solve the equation for T, the temperature. And if you got 3,913, then you are correct. And all I did was round. If you guys Googled it, sad boy hours, because you didn't do the calculation. All right. So we're gonna review real quick what we learned today. So first of all, we learned that light is two things. It can be a particle and it can be a wave. It can't be both. Well, it is both at the same time, but we can't observe both their properties at the same time. The next thing we learned was, do you glow in the dark? And well, complicated answer, yes you do, but you can't see it. Then we learned about how heat vision goggles can detect the infrared light that humans and animals emit, thus forming an image that you can see. And then we talked about the beginning of quantum theory. So this stuff is important because next time when we start talking about atoms and how atoms have emission spectra and stuff. This stuff that we learned today is really important and it builds off. So you guys might be very sad that this was more physics than chemistry, but that's okay because next time when we do chemistry class, you'll understand how to do a lot of the problems because this class gave you some of the physics background. So this is the last chance for any questions you might have, anything that you might want me to answer, and I'll open up the chat to see if there's anything you want me to address. What's after this, you'll have to wait and see. Okay, guys. I hope you guys learned something interesting today, something you can tell your parents about, like, wow, did you know you glow? That'll be fun to tell your mom and dad, but you'll have to also explain to them that you glow infrared light, not visible light. Otherwise, they'll think that you're crazy. Yes, somebody said biology class was chemistry and chemistry class is physics. And what's physics class gonna be? Biology? Who knows? I'm just kidding. I'll stop sharing right now because it's time for the next class to start. And I'll turn off the